Anyway, well, thank you for everybody that's joining us tonight, whether you're on Zoom or YouTube or finally back in the class. It's good to see everybody back in here, or at least a good chunk of you. And hopefully, with the next couple of speakers that we have, we'll have more people in here. We'll have more speakers that can be in the classroom with us too. But, tonight we're very privileged to have Dr. Debra Wallace. She is the Deputy Branch Chief for Astrophysics at the NASA Marshall, where she leads a team of 30 plus scientists working in high energy astrophysics. Now, Dr. Wallace, she started her astronomy career at the Space Telescope Science Institute with an undergraduate degree in business. And then she went on to obtain an MA in physics from Johns Hopkins, and then picked up a PhD in astronomy from Georgia State. So she's got quite the resume. She spent 3 years as a member of the Astrophysics Branch at NASA headquarters prior to joining NASA in Marshall. And when not enabling others' research, she uses multi-wavelength visual imaging, spectroscopy, and interferometry to better understand black hole and gamma ray burst precursor stars, their life cycle, their influences, and their impact. So it is a great pleasure tonight to welcome, for the first time here, Dr. Debra Wallace. Please welcome her in.
Thanks, Sean. Okay, well, y'all asked me to talk about the vast cosmic structures of the universe, which is not what I generally study, but it's related to what I generally study. So I wanted to fulfill your desires, and I thought a good place to start would be with JW and the Cosmic Evolution Early Release Science, the Sears survey image. Everything that you see, more or less, is a galaxy. There are 100,000 galaxies in this image, and it was taken between 470 and 675 million years after the Big Bang, so age of the universe. And, we're still trying to figure this out. So one of the ways that we do that is by looking at the history of the galaxies via their redshift. And here is just a gravitational map of the universe. Everything outside of the local group, which is our little group of galaxies, is running away from us. And for roughly 13 billion years, you'll get the roughly in a minute, the universe has been expanding. So the further away something is, the faster it moves away. It's like putting dots on a balloon and then blowing up the balloon. The space between the dots expands. And if you're not gravitationally bound, like our local group of galaxies is, then as the space between you expands, you're going to recede from us. So Big Bang, and then a period of inflation, and then a afterglow light pattern of about 400,000 years. So this is during the period of accelerated expansion, i.e. the inflation, and then it cooled adiabatically. There was no transfer of heat with the environment, and at a redshift of about 1100. So I'm rearranging my slides. About 378 years after the Big Bang, I think that should be 1,000. The temperature dropped to about 29.29 EV, and that's when matter and radiation decoupled. And that gave rise to the cosmic microwave background, and then electrons and protons recombined to form hydrogen and helium, which are the building blocks of the universe. And then this was followed by the Dark Ages. You could see between things. It was no longer this thick cosmic plasma, because the neutrons and the protons and the electrons had combined, i.e. recombination, but there were no stars. There was no light, because we didn't have yet the epoch of star formation. So these are the Dark Ages. And then they ended sometime between Z of 15 to 30 with the first stars. And they started producing the first photons, and that could reionize hydrogen, and that started the epoch of reionization. And this is roughly, and you'll understand roughly in a minute, 13.7 billion years ago. So the first stars at about 400 million years, and then the development of planets and galaxies, and basically the structure that we see today. And I'm not going to talk about dark energy yet. So this is the Sloan Digital Sky Survey, and often the network of what we see now and what we see in the past, because whenever you look back into the galaxy, into the solar system, into the galaxy, into the universe, what you see is really a snapshot of the light, the way that it was when the light left the object. So you're seeing the universe the way that it used to be, not necessarily the way that it is. And this is really captured here in this Sloan Digital Sky Survey image. You can see that what they call the cosmic web, because as you go deeper in time at higher and higher redshifts, you're capturing a different segment of the universe, depending on how far away something is to you. But at every epoch, and if you look here along these redshift curves, you'll see this filamentary structure, this web, like a spider web full of knots and filaments and sheets and voids. And that's really the universe that we see. And if you turn it, what you get is this upper image is really in profile, where you see all of the different distances at once. But if you look at the lower image, this is what it looks like if you take a slice through it and you're not stacking everything up on top of each other. And actually you break it out according to redshift. So this is the bottom image is a 3D slice through the network of hydrogen filaments that crisscross the spaces between galaxies, i.e. this is the cosmic web, and it was an image taken by the Keck Cosmic Web Imager. It's about 10.5 billion light years away, which is the region, and then the volume is roughly 2 by 3 million light years. It's a depth, and you can see from the bottom image the depth of about 600 million light years. And the reason we can see this, because it is a gas image, is it's being lit up by a quasar. And this is really how, for determining the structure of the cosmic web, you are able to see this filament matter, this molecular cloud, the dark tendrils that connect the galaxies, is because it's being heated and lit up by something nearby. And in this particular case, it was a quasar. And then on the right-hand side, this is a simulation. And if you look at the bottom, by Katara et al. This year, if you look at the bottom, you'll see it's really not that different than the image that's collected by the Keck Cosmic Web Imager on the top left. And so our simulations are doing a really good job of capturing the data that we actually see. So the thing that put a wrench in our understanding of the galaxy was the discovery of dark matter, but this was predicted. So Zwicky, taking a look at the Coma cluster, really predicted this far before it was discovered. In 1929, Hubble completed his study and proved that the universe is expanding. And in 1933, Zwicky suggested that the dominant fraction of mass in galaxies was something that we couldn't see. Because he measured the redshifts of those galaxies from optical spectroscopy. And then for the coma cluster, which is what this is, he measured a velocity dispersion of 1,600 kilometers per second. So that translates into a very large amount of internal energy. And then for it to be gravitationally bound and dynamically stable, i.e. not flying apart, that means that the gravitational potential energy required would be about 20 times what would have been inferred just from the stuff you see, the stars, the gas, the visible matter. So he suggested that some sort of dark matter, cold enough to be effectively invisible in the optical observations, because it would have been at a lower energy, might account for the deficit. And he was right. Vera Rubin measured the rotation curves of 10 spiral galaxies using Balmer alpha, or the H line at 6562 angstroms, in the galaxy rest frame. And her results showed that the rotation curves were approximately flat out to distances of tens of kiloparsecs. It did not show the expected Keplerian decline, and that the maximal velocity was a measure of the total mass and radius was not consistent with the luminosity of the galaxy. And so to maintain those rotation curves, something had to be providing the extra mass that would allow that to maintain that velocity. So the only explanation was Zwicky's dark matter halo to explain the observed rotation curves. Why is my movie not playing? Yeah, it's supposed to rotate, but it keeps stopping.
Everything's working.
I think it's a bandwidth issue. Anyway, moving on. So another proof of dark matter was Einstein hypothesized that a sufficiently large mass should bend gravity around the mass, i.e., it should create a distortion in the fabric of space-time that would cause the trajectory of light to bend, because space-time itself curved. And so what we perceive as gravity is really this curvature. And so you can see it here. So there is the light from the distant galaxy. Here is the massive galaxy cluster. And the light is actually bent around the massive galaxy cluster to reach Earth. And it's bent both ways. And this can either make it brighter, or it can suggest that you get multiple images like an Einstein cross. And this is another proof of dark matter, because we are seeing this. We are seeing Einstein crosses from the light that's being bent from distant objects around something massive that we can't see. So here is a cosmological model. It predicts that galaxy clusters grow at the intersection of filaments that structure the cosmic web. And here you can actually see in this Chandra image the knots that are where the galaxies are growing and the filaments that compose the cosmic web. These are composite images. It's Sloan Digital Sky Survey with Chandra in the purple on top. And it reveals the hot intercluster gas. And the optical matter is really only about 1/6 of the gaseous matter. And this is at an age of about 300 years. So it is relatively young. And this is an X-ray version of tracing, again, the arms and the filament and the structure of the cosmic web. So in order to trace that cosmic web still further, one of the things that they hypothesized was that there would be an energetic afterglow from the Big Bang. I'm not going to explain the Big Bang because I'm sure y'all all know what it is. But here is a Planck image, and you can see the knots and the filaments and the structure of the cosmic microwave background. It is the oldest light in the universe at about 380,000 years old, and the anisotropies reveal the tiny temperature fluctuations, and they are really tiny, a few parts per million, and they are regions of slightly different densities and the seeds of all future structure. This is really how we got the cosmic web that we have, the creation of these stars and galaxies of today, were those tiny little fluctuations, those tiny little seeds in the early universe. So, a few notes, and I'm going to quickly go through all the text. Cosmic microwave background, it has a thermal black body spectrum, which is in the top part of the graph at a temperature of 2.72 Kelvin. And variations in intensity are expressed as variations in temperature. So it's very uniform across the sky. It's very unlike what we see in the visible matter for stars or clumps of stars. And it is isotropic, i.e. the same everywhere, to roughly 1 part in 25,000. Standard variations are just about 100 millikelvin. So there is a slight motion because of the motion of the sun as it moves within its local group in the universe, but it also has a polarization, a variation, and it is moving out, as you'll see in a second. It has, the cosmic microwave background has the vast majority of photons in the universe by a factor of about 400 to 1. And the number density of photons in the cosmic microwave background is 1 billion times the number density of matter in the universe. Without the expansion of the universe to cause the cooling of the cosmic microwave background, we would still be in a plasma. The night sky would shine as brightly as the sun. It would never get dark. And we wouldn't be able to see the matter. So, what we have learned from observations of supernovae is that the mass and energy set the curvature of space-time, but space-time sets the geographical map of curvature for mass and energy. And two groups got the Nobel Prize in 2011 for physics for discovering the expansion of the universe. And it was really funny because I worked at Space Telescope when these groups were doing their research, and they hated each other. They wouldn't even sit at the same table. They wouldn't look at each other at lunch. It was extremely competitive. But both teams ultimately showed that the universe is not slowing down, it's speeding up. Type 1a supernovae have the same intrinsic maximum brightness, and they're considered standard candles. And so if you measure the peak brightness in the light curve, the fading of the light tells the astronomers how far away they are. So supernovae that exploded when the universe was about 2/3 of its present size are about 25% fainter than would be expected if the rate of expansion were decreasing, which is what you expect, right? You expect for an explosion that things explode out from the source, but as they run through atmosphere or interstellar medium, they're going to slow down. And then eventually it's going to recollapse like a baseball you throw in the air that eventually falls back to Earth. But what they've decided is that there had to be some reason that the expansion of the universe was increasing, and that they came up with dark energy, or, well, really Einstein's cosmological constant. And this is the theory of what's fueling the expansion. So for most of its first 500,000 years, the universe looked extremely different than it does today. It wasn't speckled with stars and galaxies. It had this sea of plasma of charged particles, and it was dense, it was uniform, it was fluid, and there were very, very, very small perturbations. It was incredibly uniform. What variations there were took the form of slightly denser kernels of matter, and these were rare. The clumps had more mass, so these slightly denser kernels of matter eventually attracted additional material because, you know, gravity works. So though there was a hot plasma initially, and the particles in the hot plasma just bounced off each other, eventually, as the universe cooled, the gravitational pull and the collisional repelling were no longer, the collisional repelling was no longer as dominant. And this created waves of pressure and sound that propagated through the plasma. As the universe cooled and the baryons, the neutrons and the protons, combined with the electrons to form neutral atoms, the waves ceased because the collisional repelling stopped, but that you could still see the legacy of the ripples, like impressions in sand once the wave is gone. So when the atoms formed, the ripples froze in place, and this allowed them to carry a little bit more matter than the average across the universe, because just like that ripple in sand, if you spread something across it, within the little divots in the ripple, you're going to be able to put slightly more material. And gravity became the dominant force in the universe. So over the course of hundreds of millions of years, clumps from plasma that once filled the universe gravitationally accumulated more material, and they became stars. And then those stars clung together by gravity and formed groups. And then those groups formed the galaxies, and then the clusters of galaxies that we see today. And slightly more galaxies formed along the ripples than elsewhere because those ripples had slightly more material. Let's see if the movie plays.
Immediately after the universe was born, it was too tiny and too hot for protons, electrons, and even photons to exist. Within a second, it had expanded and cooled enough for protons and neutrons, collectively called baryons, to form. Almost instantly, it was a rapid burst of sound waves triggered by tiny variations in this particle soup. Scientists call these waves baryon acoustic oscillations. The pressure waves traveled outward for 400,000 years until the universe thinned and cooled enough for light to travel through it. The universe became transparent and the waves froze in place. Over time, the denser regions formed by the waves encouraged more star and galaxy formation than other areas. The imprint of those waves expanded with the universe, slowly accelerating due to dark energy. Today, with our snapshot of the universe, there is a slight tendency for galaxies to be separated from each other by a distance related to that expanding ring radius. Although difficult to see, it is detectable as a slight bump through careful surveys of many galaxies.
So now those little ripples that held more material, those are the filaments and knots that preferentially form the galaxies that we see.
Immediately after
Nope, let's keep going. So they use what's called baryon acoustic oscillations which are leftovers from the imprint of the pressure waves, to determine the value of the Hubble constant, i.e., how old is the universe? So the waves didn't propagate after the era of reionization, but those frozen little ripples stretched as the universe expanded because of the expansion of the universe, increasing the distance between galaxies. So if the galaxies weren't gravitationally bound, then the expansion increased the distance between them. And so galactic positions at different times reflect how the universe has expanded as a function in time, because obviously those little bubbles are going to be smaller the further back you look. So as the movie said, scientists have noticed a pattern in the way galaxies cluster together. We are more likely to find another galaxy today about 500 million light years away than slightly nearer or farther, simply because that's the size of the bubble. If you look out into space at higher redshifts to earlier cosmic times, this distance will decrease because the frozen BAO ripples are going to be smaller. So the DESI survey, the Dark Energy Spectroscopic Imager survey, is looking at these ripples and using it to determine an age of the galaxy, which is the same data that Planck used earlier. The first year data results are now in preprint. They've measured the expansion rate of the universe out to 11 billion years in the past. And they've used these little bubbles and the oscillations and the ripples to determine a value of the Hubble constant. And what they're using is called Baryon acoustic oscillations, or BAOs. At extreme distances, the BAO pattern is too faint to detect, but they can look at the shadow of the pattern because it's backlit by extremely distant bright galactic cores known as quasars, which is what showed up earlier on the image I showed you of the Chandra structure, the filaments and the bubbles and the structure that's mapping out the gas around the coma cluster. So this allows us to really map out the pockets of dark matter, of dense matter. So DESI is actually operating on the Mayhall telescope at Kitt Peak. It's a project that's funded by the Department of Energy. And they are trying to use BAOs as a standard ruler to really measure the expansion history of the universe. So the first year data have come out, and it allows a measurement to be made. Roman, which NASA is building now, is going to really increase our ability to do that. It's going to go 5 times deeper than originally planned, out to about 600 million years age of the universe, so about 4% of its current age. And it's really going to allow us to hone in on the age of the universe and how it evolved as it grew after the period of recombination. So this is just it's a map from the DESI data. And you can see as you go deeper or higher redshifts, the structure really changes. Everything's a lot closer together, but the overwhelming spider web, cosmic web is very apparent. And this is just the first year of the DESI survey. So it goes out to about 11 billion light years, and every point you see is a galaxy. So what you see on this particular slice is about 600,000 galaxies. But this is an insignificant portion of what the survey captured. This is just another example of more or less the same image, the same data that I showed you before, with the dark matter filaments and the seeds that really are forming the lines of the filaments. So those initial slightly increased mass elements really formed the seeds that have grown to form the halos of dark matter. And on large scales, the pattern of galaxies we see really matches those seed perturbations. It matches those the size of the circles in the early universe. On small scales, though, gravitational effects and local dynamics really they have a significant effect on the distribution of galaxies, simply because they're gravitationally bound. So this is a light green arrow on the right-hand side. It shows the orientation of the intercluster filaments, and this is based on weak lensing signals. And then you can see the cosmic web filament directions detected with the galaxy distributions in the magenta and the purple filaments. But these are well aligned with the galaxy-based large-scale filaments. And really all this means is that galaxies tend to align themselves with the dark matter filaments. So here is a constructed image from ESA's second release of the Gaia star map and the Planck dust map. And you can see it here again. If you look off of the edge of the galactic plane, you can see really the filamentary structure in the purple outlined with the voids, and ignore the yellow, with the voids and the wisp and the sheets. Even in this image. And here's the same image from Euclid, which is a ESA satellite. There were 260 observations in 2024 between 25th of March and 8th of April. It was 132 square degrees of the southern sky. And this is obviously a false color image, but you can see again the wisp and the tendrils and the filaments in the galactic structure. And those tend to be very aligned with the structure of the visible material. So where you live actually does matter. There's a close connection between the morphological components of the filaments and the knots with the material that we see, the bright material, the light material. Clusters sit at the intersection of the filaments, and filaments are formed at the intersection of the walls. And so the filamentary nature of the environment has a distinct influence on the shape and the spin of the dark matter halos. They tend to align. There's weak alignment of the galaxies and filaments. They orient themselves the same way. Void galaxies have a lower material density and have atomic hydrogen masses that are nearly 2 times lower than their average density counterparts. They're bluer, they're less massive, they have later morphologies, their star formation's affected. And the star formation rates are higher than galaxies in denser large scale environments. Plus the rate of star formation is different. Meldorf in 2023, he found a correlation between supernova brightness and the overall dust content of the galaxy. And so supernovae may not be as indifferent to location and as robust a standard candle as we currently think. And then galaxy stellar mass correlates with the average galaxy metallicity. And by metallicity, I mean anything that's heavier than helium. Astronomers have a slightly different definition of metallicity than the rest of the world. And then metallicity is very important, as you saw earlier in your picture that I missed, unfortunately, of the Wolf-Rayet star, because it has a strong effect on the evolution of massive stars because it drives their stellar winds. So, superluminous supernovae are characterized by low metallicity, and a short-lived stellar population is required to regulate the superluminous supernovae production, which means that, again, supernovae are going to be affected by the environment of their galaxies, their host galaxies. I am not going to talk about this. This is just the velocity web for the local supercluster, and you can see that the mass tends to congregate along these filaments and follow filamentary lines. They're just really studying how you can use mass velocities to track the flow of material within the local supercluster. And it's consistent, as you can see from the video. Everything's funneled to the high gravitational potentials, and it is stretched over large distances. This is 1 billion light years, and it's all moving at roughly 23,000 kilometers per second. And this is it again. Here, this dipole repeller, things are moving away from it to the shapely attractor. And this is more or less consistent with the direction of the local group's motion as the universe expands. So the flow of material tends to be aligned with the direction of motion of the local group. See? So you have two methods. We've talked about how you're going to use supernovae to establish a cosmological distance scale. And we talked about how you're going to use baryonic acoustic oscillations to establish distance scale. And so both of these lend support to what's become the standard cosmological model. It's a spatially flat universe with an energy budget today that's about 5% baryonic matter, i.e. protons and neutrons, 25% cold dark matter, we don't know what it is, and 70% dark energy, and that's roughly consistent with Einstein's cosmological constant. And then you have smaller contributions because you have massive neutrinos and you have radiation. And so all of these constraints are consistent with the standard CDM cold dark matter cosmological model. with a cosmological constant. Reese et al. 2021 found that adding up all the JW measurements, including a correction for the low sample of supernovae data, were consistent with his earlier findings for the Hubble measurements, and that they got a value of the Hubble constant of 72.6, which translates into an age of the universe. And so that's really consistent with what he got originally of 72.8 for the Hubble, from the Hubble data. Planck used BAO data to establish and age the universe as 13.79 billion years old, and they got a Hubble constant value of 67.74. So these are radically different, and that has been come to be called the Hubble tension. There are recent gravitational wave results from LIGO Virgo, which is an NSF funded ground-based interferometer, gravitational wave interferometer, and they suggest a value of 72.77. So very consistent with the JW and the Hubble results. Not quite as consistent with the Planck results from the cosmic microwave background. So the Dark Energy Spectroscopic Consortium, when they did this and released their recent results, including all of the data from the Dark Energy Survey year 3 to derive the Hubble constant, got 68.4 with a 0.4% precision, which is very consistent with the Planck results. That's a problem because they don't add up. But not only did DESI results confirm that the expansion of the universe is speeding up, but they also suggested that dark energy, whatever that mysterious repulsive cosmological constant is, the force that drives the process, that it's not constant, that it changes, which would explain the difference between the Hubble results and the Planck and the DESI results. But the results aren't confirmed yet by peer review. And there are scientists who've already weighed in that suggest that while the BAO measurements by the DESI people, oops, that should have an I, lend support to evolving dark energy, it needs to be fully studied. It needs to be investigated further. The results need to be peer reviewed and reproduced, and I agree with that completely. But one of the co-authors says, if we are seeing hints that the dark energy field's been changing over time, it is not what the standard model of cosmological constant dark energy suggests. And so it goes out the window and we get to start from scratch. And that means revising our understanding of physics, our understanding of the Big Bang, and our understanding of, what's going to happen for the universe. And it means that there may actually be a big crunch. It may be that the universe doesn't expand forever, that it eventually turns around and starts contracting again. So Hubble and Webb measurements confirm the universe is expanding 8% faster than early models, which would be represented by the BAO and the Planck data represent. The Webb data confirms the Hubble results. And so we're left with, well, what are some possible explanations? There could be stellar crowding, which I definitely believe is going on. There could be metallicity effects on stellar evolution. Again, very likely, since massive stars' mass loss is driven by metallicity lines. There could be changes to gravity. Maybe gravity is evolving. it could be that the DESI folks are right and there is a evolving cosmological constant. It could be that there are undiscovered particles. It could be that there are changes in how matter is distributed as the universe has expanded. So either something's wrong with the measurements or something's wrong with our understanding of physics. And, you know, it'll be interesting to see this year as those DESI results get peer reviewed about what will happen. So, and then I had a little lagniappe for y'all, a little something extra. This is what's going on in my group and how we're making contributions to solving these issues. So first is the biggest thing that's come out in the last several years of astronomy. It is IXP images, and IXP is an X-ray polarization observatory that's designed to work with the Chandra telescope and other X-ray imagers that really lets us understand the magnetic and electrical fields around objects that are bright in the X-rays. So for example, black holes. And you can see here how the image is going to change in the IXP data, depending on what's happening to the thing you see. So here is a black hole. Here is the image, and I'm going to play the video if it lets me. Play the video. Can you see the video? Is it playing? It's slowly. It's okay. I'll talk about the video in a second. So for me, it's done. Is it playing for y'all? Slowly. Are y'all done? No, it's still going. Okay, I'll wait. I know that we're looking at a black hole here. Yeah, this is from the Event Horizon Telescope, and you can see it actually maps out the magnetic and electric field lines through the polarization image. And this, oops, is an IXP image. No, I don't want to install Microsoft Pro right now. So this is the IXP image, and you can see that the field lines are very consistent with a very strong magnetic field rotating in the torus around the black hole. This is the Crab pulsar. And this is from the explosion of what may have been a Wolf-Rayet star. And this really is IXP, which is allowing us to understand magnetic fields and how they evolve and how they're structured relative to the central source for the first time. Because the only magnetic field measurements, the only polarization measurements that were made up to now are from observatories launched on rockets. So you didn't get very long. And so actually I should switch them. I'm going to go forward and then back. And so Superhero is actually a science case of what we want to do. We want to look at the hard and the soft X-ray observing X-ray emission from, again, this is a black hole, but from things like the Crab Nebula. What are the physics of supernovae? How do they grow? How do black holes grow? How does this influence galactic evolution? And then there's, this unresolved cosmic X-ray background. Where did this come from? What is that about? So we are launching a balloon mission, which NASA has funded, as part of our development of higher angular resolution optics. You probably don't know, or you may have forgotten, that Chandra was actually developed at Marshall Space Flight Center. And so we have a long history of developing high resolution X-ray optics. So we've gotten funding from NASA headquarters to build Superhero, which we'll put on a balloon, and we will use it as a test bed of high resolution X-ray optics, following on for Chandra for the next great observatory in the X-ray regime. And now I'm going to go back. One of the other things we're doing is Starburst. It's a multi-messenger Pioneer. Pioneers are NASA's missions that cost $20 million or less. And this is really going to help us understand the evolution of the early universe, because this looks at gamma ray burst, and particular gamma ray burst in association with gravitational wave detections. This is going to constrain the progenitors of those gamma ray bursts, the super gamma ray burst, probe what's going on with neutron star mergers, constrain the neutron star equation of state, and then it's really going to allow us to better understand the outflows produced in neutron star mergers. And I would given that most massive stars are binaries, given that binaries exhibit this double lobe structure that you see in the top image, I would suggest that observatories like this are really going to help us understand how massive stars evolve, and how massive stars evolve differently based on different metallicities. Because the earlier you go back, the earlier you go back in the age of the universe, the higher the redshift, the lower the ambient metallicity that the massive star formed from. Simply because, the later you go, the more stars explode, the more they're seeding their environment with heavy metals. The earlier you go, it's more of a pure hydrogen and helium. So this is a little about what we're doing here. And you can see here's New Star and here's Superhero. So this is what New Star saw. And this on the right-hand side with less than 10 arc seconds imaging capability in its full width max. This is what we'll see, and we'll be able to see all of the filamentary structure around the crab, and really what is funneling the X-rays and the magnetic fields that we see with IXP. And that's just my references. So I'm going to stop sharing, and if y'all have questions, I am happy to take them. Okay. Thank you.
If anybody has questions, I can pass around the mic too, so we can hear you out. Zoom in the YouTubes.
I'll ask a question.
Yeah, sure.
I'm the least informed person here, I'm sure. Is there any way theoretically to ever know if the Big Bang and the expansion and the possible collapse has happened before?
Mind blown.
I don't think so,
Nothing in matter that would.
simply because
show what
when
history-
you collapse down a massive star to a black hole, you're obliterating all of the elements. And the only way that we would know is by by looking at the metallicity, by looking at the abundances. And so if it happened before and it collapsed back down to a singularity, and then it did it again, you're erasing all of the evidence of anything that happened before.
Yeah, guess we'll never know.
Well, yeah, I mean, the only thing that comes out of a black hole allegedly is Hawking radiation. And that's at the very end of the universe. So there's really nothing that, once it goes in there, it pretty much stays put. And I guess, I guess at the end of a black hole, as it emits this Hawking radiation, that it is, I guess that maybe you could theoretically reassemble that, but it goes over trillions of years. So I don't know, I'm not the physicist here.
Once you get there, stroke the etch a sketch.
Right.
It's gone.
Hi, can you hear me?
Opinions.
She can only hear you from that, but that's for Zoom. That's for Zoom and YouTube.
Sorry.
So she just talk loud.
Okay, so my question goes back to the ripples. And the ripples were happening until about 400,000 years into the universe's existence.
Things recombined.
Okay, so I'm curious, why did the ripple movement stop at that point and expansion was still happening? Was expansion happening all the while?
No, because you had gravitational pressure, but it was also hot enough and things were soupy enough that all of the photons kept bouncing into things. And so there was collisional pressure. And so as it cooled, you probably know, as you heat up anything, except for water, the atoms in the fluid are going to get more and more excited. They're going to travel faster and faster. They're going to have more and more collisions. And as things cool, then they don't travel as fast. They don't move as quickly. They don't have as many collisions. Things settle down. They're able to combine into atoms, and that locks up a lot of the material that they were bouncing into. And so as the universe transitions to what we call something that is transparent, i.e. photons can easily exit, there's not as many, there's not as much collisions happening, and it slowly becomes less of a plasma and more transparent. And then eventually those individual little baryonic acoustic oscillations, the little bubbles that they're forming at the beginning, they're going to, like I was saying earlier, you're going to get a buildup of material where those little ripples happened, simply because they're minutely less flat, less, they're going to have a little bit of extra material, and that's what's going to form the seeds for the galaxies and the stars and the stuff that came later.
Make sense, Claire?
Yes, thank you.
Oh, we got one over here. You want to pass the mic down?
I'll take this down so you can hear me. What is the intersection of what you're doing with AI in terms of determining what's wrong with your measurements versus what's wrong with physics? Are you using AI in this type of research, or where is that development heading in terms of changes to gravity, the evolving cosmological constant?
They just published this. So we'll see. It hasn't even been peer reviewed yet. But they are using AI in the models that simulate what they see for the infrared background. And they're using machine learning to try and get a better handle on it. So yeah, I mean, stay tuned. I wanted to leave you guys with a cliffhanger, and this is it, because the DESI results, they just came out this year. They haven't been peer reviewed yet. They are consistent with the Planck results, and they are not consistent with the supernova results. So there's still that tension, and we'll see. I personally think that, if you want my personal opinion, both of them are flawed. I think the supernova results, anytime you look, so 1 arc second at the distance of the sun is huge, right? I mean, you can totally differentiate between two objects. 1 arc second at the distance of Andromeda, and you have a huge space that you are using. I do not think they are seeing individual stars, especially given that massive stars tend to form in groups and pairs. So I suspect that there is a problem with the supernova data. And I think that as we improve the simulations, we'll get better at resolving the BAO data.
Anybody else have any other questions for Dr. Wallace? All right, I think that's a wrap. Thank you, Dr. Debra Wallace. Don't forget,
Enjoyed meeting y'all. Thank
oh,
you for hosting me.
thank you. Don't forget, we got Dr. Kevin Green next month back here live in the classroom. So we hope everybody will join us then. Thanks again, Doc. Thanks
Thank
everybody
you.
in here. We'll see y'all soon. Yep,
Yes.
there it is.
All right.
You're
Thanks.
free.
Bye-bye.
Appreciate it.
Good night.